So good morning and welcome to the Grayscott Thursdays. Grayscott Thursday is a series of webinars we organize every Thursday at 10 on various HPC topics, such as this one today on Python, which will be presented by Alice Faure and Jean-Marc Colley, who will be introduced later on. But first, let me give you a little presentation of the organization team. So there is Pierre Robert, a research engineer from the LAP, French Laboratory of Physics and Particles in Annecy, and Karim Azoum and I from TerraTech, and within the French NCC called CCFR, and with the LAP of Annecy, we co-organize the Grayscott Thursday and the Grayscott School. Because those 17 Grayscott Thursdays you will discover are held by 9 incredible teachers who will each one of them give you webinars on their topics, introducing at the same time the program of the summer school. So what is Grayscott School? It's a free summer school dedicated on programming and optimization on heterogeneous architecture. It was created 2 years ago by Pierre himself with a few people in Annecy. And we, the French NCC, joined him last year to help him develop it not only in Annecy, but also in 12 satellite sites among 4 countries. So this satellite site helped us reach more people by broadcasting the school live in their locations. And that's what we're going to talk about today. So the summer school had a 2-week program, 1 week CPU and 1 week GPU, but everybody was free to choose the courses they wanted to attend, thanks to our a la carte option. And we finally trained over 500 people, and everything is available still on replays on our website and YouTube channel. So you can access it if you want, but everything was in French. This year, obviously, we are going European, so all will be in English, like this webinar. You have various ways to attend the school, as you'll see in the video I'm going to launch for you. And also we invite you to be part of the team and become a satellite site yourself if you want to host the school at your place. We are able to provide you everything, all courses, containers, access to the teachers, and also to connect you with our growing HPC community. So let me now play the video for you, and then we'll start with the webinar.
Do you sometimes feel limited by your resources or unsure how to maximize the potential of your HPC resources? Imagine a place where collaboration, creativity, and learning converge with high-performance computing. Welcome to Grayscott School 2025, Europe's leading summer school for HPC. Taking place from June 23rd to July 4th. Over 2 weeks, students, academics, and industry professionals from across Europe will explore the frontiers of programming while building a vibrant community. Together, we'll discuss programming and optimization on heterogeneous architectures, highlighting their respective characteristics and limitations. You'll have a unique opportunity to explore generic optimization methods, as well as the latest technologies and languages for achieving optimal performance. The school is free and open to everyone, and you can participate in person in Annecy, France, with the teachers, at one of our satellite sites in Europe, or online via our live streaming. You can choose from an intensive program or a la carte courses to develop your skills at your own pace. With the first week dedicated on CPU and the second on GPU architectures, you will study computational accuracy, vectorization, parallelization, compilation, memory profiling, unit testing, and the various programming languages C++, Fortran, Rust, Python, and Julia. In addition, we will study the MPI, OpenSHMEM, OpenMP, TBB, EVE, Kiwaku, Sycl, Thirst, CUDA, OpenACC, Vulkan, NumPy, Numba, QPy, CU-numeric, JAX libraries, and Legit, as well as computation with PyTorch and TensorFlow, and the G++, Clang++, NVC++, NV Fortran, G Fortran, and DPC++ compilers. Throughout the course, you'll discover and use profiling tools such as Valgrind, Perf, Macau, Insight, Malt, and NumaProf. Each session leads to a practical challenge, the simulation of Gray-Scott's diffusion reaction, which tries to describe how a chemical reaction evolves over time. Simple to understand, but complex enough to push the limits of optimization. Thanks to our specially designed Docker containers, you'll have access to a complete working environment to follow courses and exercises on your laptop or supercalculator. Throughout the program, you'll be guided by a dozen expert instructors, leaders in the field of programming and HPC. You'll have the opportunity to ask questions and chat with them live on Discord, so you can tailor your learning to your needs. Join our growing community of over 500 users to find answers, exchange ideas, take on challenges together, and build bonds that will last well beyond the program. You can also join the Gray-Scott School European network of satellite sites, not only to attend the courses, but why not become a satellite site yourself and host the school in your location? You just need to provide a room, a contact person, and access to computing resources. We'll provide courses, tools, and Docker containers for a seamless learning experience. Gray-Scott School is free and open to all. It's your chance to master advanced programming and optimization, engage with a growing European HPC network, and push the boundaries of technology and training. You can kickstart your journey now by joining Gray-Scott Thursdays, a free webinar series previewing the school's courses. Don't miss out. Register today to attend, whether in person in Annecy, France, or at one of our satellite sites in Europe, or online via our live streaming. Gray-Scott School 2025, where HPC meets your potential.
Thank you for watching the video. If you have any question regarding the school, you can ask them in the Q&A, and Pierre and I will be glad to answer you. Thank you for listening to me, and now it's time to give the floor to Pierre Aubert, who will be able to introduce our speakers today.
Okay, thank you, Marie. So today we have the privilege to have Alice and Jean-Marc for the presentation about Python programming on CPU. And so I will start with Alice. So Alice is working on CTA, is a research engineer on CTA. She works at ILUPM, and she is involved in the simulation of the particle cascade that we can have to simulate the particle cascade on the atmosphere for CTA. So it's a lot of work and a lot of work to optimize it on CPU and GPU. And Jean-Marc is working on Garroum, which is an experiment, radio detection experiment, as you may know, maybe LOFA or SKA, for example. And ZTF also for large field astronomy view. So it's a Zwicky transient facility experiment, and it's involved mainly on data processing and data analysis side of the coin. So Alice and Jean-Marc, I'll give you the floor, and I wish you a nice webinar.
Thank you, Pierre. So in this webinar, Jean-Marc and I are going to present the Python language and how we can use it to do scientific computing on CPU. Well, I can start. Okay, so Python is a very well-known language because it's general purpose and it's open source, and it's also very flexible. It has a vast ecosystem with numerous specialized libraries. And well, probably you know already Python because it's one of the most popular languages, particularly in education and research. And it's also widely used in machine learning, data analysis, application development, and we can also use it for scientific computing. And we're going to see in this webinar how we can do it. So the principle of the Python language is that most of the time we use it as an interpreted language with its interpreter CPython. And so if we use it as an interpreted language, it's not going to be compiled into machine code like C, Fortran, C++, for example. And instead, the source code is going to be compiled into bytecode, which is an intermediate format. and this bytecode will be read and executed line by line by the interpreter. So this makes for a slower code. It's slower than compiled code, but it's more flexible and it's also easier to use. And as you may know, Python is also dynamically typed, so you don't have to specify the type of the variable that you declare. So it's very easy to use. And you can use it for a bunch of things and for object-oriented programming as well. So let's delve into the history of Python to understand why it's like that today. So it has been around for more than 30 years. It was first published in 1991. It was created by a Dutch developer whose aim was to get a clear and easy to learn language. So it was really the point of the creator to make it easy to use. So he summarized its philosophy in the Zen of Python. I think you have the slides on the Gray Scott website, so you can click on the link. And right now we are in the 3.13 version, which is the latest stable release. We are still at the version 3, the major version 3, which was the latest major version of the code, which was published in 2008, so a long time ago. In this 3.13 version, there are some experimental features for performance tuning, such as a free threaded mode and a JIT compiler that you can test if you're interested. How can we use Python for scientific computing on our CPU? Well, one thing to have in mind is that most of the calculation libraries that we use in Python regularly are written in C and compiled. So for example, numpy, math, etc., they are actually compiled. So the only slowdown you get when you call them is the fact of calling them by the Python code. But the code inside the library is very fast. So a simple way to get fast Python code is to spend most of the computation time using these optimized libraries. And we're going to see it also in the end of the webinar. It's also possible to use compilers for subsets of the Python language, for example, Numba, to speed up your Python code. So in this webinar, we're going to see mostly NumPy and Numba. And in the Gray Scott's Python CPU course, we will learn with tutorials how to write fast Python code and to optimize it for the CPU. So maybe before we jump into NumPy, I'm just going to introduce two tools to profile and benchmark your code. So the first one is a profiler that you can use to identify the hotspots of your code and where it slows down. We recommend to use PySpy, which is a sampling profiler for Python programs. And what's good with PySpy is that you can profile multi-threaded and multi-process code. So here we give about the installation instructions and also some useful options. So you install it with pip. And then you can record your code without having to change it. You can profile it. And so, for example, if you use the speed scope format, when you profile it, you can produce a profile that you're going to open with the speed scope app, which is very convenient. So on the next slide, you can see that this is the profile obtained with PySpy and opened in SpeedScope. And so you can see the functions and the different calls, the full flame graph of the code, and it's interactive. So you can, when you use it in SpeedScope, you can click on the function, etc. So it's very, very easy to use. Okay, so this is to profile your code, so to find where you have some slowdowns. But once you have identified it, if you want to change some function of your code that is too slow, and then you want to compare it to another function that will be faster, you have to benchmark your code, so to have very specific measures of the timing of your code or your function. And so for that, we recommend to use the timeit module. So it's a module that helps you to measure the execution time of fragments of your code. And it's very convenient because it has a shortcut in Jupyter Notebook that is %timeit, and it also determines automatically the number of repetitions of the timing that is going to be performed. So we recommend to use it, and we are going to use it in the Grace Code School because it's very, very convenient. So now I'm going to leave the presentation to Jean-Marc, who is going to present you NumPy.
Thank you, Alice. Now I am going to tell you about the NumPy library. NumPy library appeared in 2026. It's now a standard for numerical calculation in Python for at least 3 qualities. Free software and integrated into a real programming language. Clever interface to handle array. Fast. Use efficient low-level library exploiting SIMD instruction. And over 500 functions covering the following areas: term-by-term operation, linear algebra, random generator, fast Fourier transform, element search, sorting. We will present the data structure of NumPy, the notion of universal function. Then they will see 4 techniques to use NumPy efficiently: broadcasting, in-place calculation, reduction functions, selection functions. And finally, we will see multi-threading and numerical backend. So NumPy manipulates 3 data structure: ND array for multidimensional array, matrix vector, and a structured array. The elements of ND array have all the same type, are correctly aligned in memory to use SIMD. ND array can represent image, time series, spectra, or any other signal. Vector and matrix are in fact ND array of dimension 1 and 2, representing a point in a vector space and a linear application. The structured array gather heterogeneous ND array with a name column system. It can represent the parameter for different realization, such as metadata associated with a signal, like date, location, direction. Within the array, you can do term-by-term operation, like addition, multiplication, apply selection, reduction function. On matrix vector, you can apply specific function for linear application, like matrix vector product or calculation of eigenvalues. As we have seen, ND array is a central structure of NumPy library, defined as a class. Important attributes are shape, content, number of elements in each dimension. D-type, it's a numerical type like float, integer, and N-types for total memory occupation. The example of method, reshape method allow you to redefine the shape of the array. As type modifies the element type of the array, and copy duplicates the array memories. Universal function is a family of functions that share common properties. Can be applied on 1 or 2 ND array and return ND array. Operate element by element. The binary functions accepts ND array with different types and applies the same casting rules. The binary function accepts ND array with different dimensions if the broadcast rule can be applied. See further. Over 16 universal functions defined in NumPy, like multiplication, addition, sinus, square, power, and so on. Example of functions that are not universal: basic statistics, max, mean, variance, modify shape of array, swap axis, squares, reshape, assembling array, vstack, hashstack, logical function or any is closed, search and select function like where or take. For the next slide, we are going to focus on the broadcasting, which is the central concept of NumPy. The out loop, it's a loop that has the processing that is executed the most of time. It's the innermost loops. Using a Python loop for out loop will be very slow. Broadcasting concept allowing you to avoid writing Python loops. The simplest broadcasting is the multiplication of all array by a scalar. In the example, I have a little array with 3 numbers and multiply by 10. And in output, all elements I multiply by 10. NumPy know that it must multiply all elements by 10 without writing an explicit loop. Another example, let's now take an array of 10 images that we want to calibrate individually with a scalar. Each image has its calibration coefficient that we store in an array of 10 dimensions, of 10 elements. Try to do this with the same simple syntax, vector multiply array of image. So it returns error. Value error operand could not be broadcast together. So what are the rules of broadcasting? 2 rules. NumPy compares the dimension of the 2 arrays starting from the right. The second rule concerns the number of elements in a common dimensions. If the dimensions are equal, no problem. If one of the dimensions is 1, it is stretched to match to other. Otherwise, NumPy writes an error. In a previous example, the dimension 10 of the calibration vector is compared with 300, which is the size of the side of the image. So it's not compatible. What should we do? Solution 1. Return to the case scalar multiplication with Python loops. Or use broadcasting required to modify the shape of array. Solution 2, you can modify the shape of the image to put 10 to at right. Solution 3, you can modify the shape of coefficient, adding 2 dimensions to have 10 at left. Before we start writing the code, let's introduce 2 important concepts. In-place and out-place definition. In-place processing is performed over the data in array and the result are stored in the same array. Out-place processing are performed on data from array and the result are stored in another array. So start to solution 1 as with a naive loop as a reference code. So we write the out-place version, and we will see the in-place version later. So the function start by a copy of image, write a loop, and multiply each image and return the copy of with calibration. Solution 2, we will modify the shape of the image array to satisfy the broadcasting condition. So we have a 3 function modifying the order of the dimension. Transpose, reverse the order. Swap axis, simply swap the 2 axes in parameters. And move axis, insert and shift the axe to the left. You have an example in the slide. So we write the solution 2 with swap axis. We write the out-place version 2. And result must have the same shape, so we need to apply 2 times swap axis. 1 time to satisfy the broadcasting, and 2nd time to return to the good shape of the array. To write the solution 3, we must define the notion of a new axis. We have a 1D array A with 3 elements, and a 2D array with 3 columns. In fact, it's legitimate to be able to consider a 1D array, like A, as a 2D array with a single row. This point of view doesn't require introducing additional data. With NumPy, this is possible with the notion of new axis, which increases in the array by 1 dimension with single element. NumPy function extend dims do the same thing. In the example, you have the way to use new axis in the bracket. We can write solution 3 now. So from shape 10 to shape 10, 1, 1, we need to apply 2 times new axis at right. Notation instead of a new axis keyword, it's possible to use none. So the outplace version is very short. Return coef bracket 2 points, comma none, bracket multiply image. This is the solution we see most of the time because the syntax is short and clear. Now that all versions are written, we need to check that they give the same result. NumPy provides all close functions which compare term by term all the elements of the array. So we have the code to compare the three results. Namely, you can find this warning in NumPy documentation about memory consumption of the broadcast. Keep in mind and do your benchmark with a realistic data size to avoid a scaling issue. You have a reference in the NumPy documentation about this warning. Now let's look at how to write this free solution for the in-place version. B equal A. When we write B equal A, B it's a reference of A, not a copy. It's a Python feature. When you write line equal A bracket 0, 2 point bracket, line is an example of a view of in the array. It's not a copy. It's a NumPy feature. There are no duplication memory between A and line. Transpose new axis, swap axis function return a view of array for recent NumPy version. So you can do broadcasting with the view if necessary. For the in-place calculation, you have the classical in-place arithmetic notation, plus equal, minus equal, multiplication, and so on. We have also an in-place feature for the universal function with the parameter out. We have an example with a sinus function where you can specify the output where the result will be stored. So if you choose the same array, it's in-place calculation. We can now write the free version of the calculation in place. As you can see, there are no return instruction. The output is a variable IMA. In red, you have the timing for the outplace function version, and in green, timing for the in-place function version. So we can see the out in-place speed ratio is 2 or 3. The loop broadcast speed ratio is 2, and the global ratio is 4. Here, another type of broadcasting, add a vector on each column on an array, as in the figure. Here we have the free outplace version as previous example. But here, instead of sweep axis, we use a transpose function. Now the in-place version, so the result is in variable A. We find the same speed ratio between in-outplace version as before. Broadcast loop speed up is 4, and globally, we have a speed up between outplace version and loop in place version is around 10. Last example with sinus AX plus B, where X is a big array. We have a free version with 1, 2, and 0 copy. We use the in-place feature of a universal function with parameter out. And the speed ratio between out and full in-place is 2. So as we can see, broadcasting and in-place processing are important concepts to master. Now let's move on the reduction function. A reduction is an operation that summarizes several values into one, like sum, average, max. NumPy implements a mechanism to iterate through elements to avoid watching a loop with the axis parameters. Axis equal n indicates that the reduction loop is along the axis n. The return array, the size along axis n become 1. By default, this axis is squares. The return array lose this axis. Parameter keep dims equal true prevent this. We have a little example to sum the column of a 2D array with this option keep dim and without and with. Another area where NumPy provide a functionality to avoid writing Python loops is a selection of elements from an array to make another array. So two ways. You have fancy indexing. You can put instead of an index or slicing an index array, 1D or 2D or list, to collect elements in array. You have an example to collect maximum of line in a 2D array. For large array of index, use function take along axis. This function is compatible with the output of argxx family, like argmax, argmin, argware. And example, we have a syntax of this function. And now multi-threading and multiprocessing. The reference Python interpreter use a GAL, global interpreter lock. This is a lock to protect all the objects it manipulates against a concurrent access. This prevents multi-threading in Python, except for I/O. In general, to do parallel computing in Python, you have to fall back on multi-processing, for example, with the dedicated module multiprocessing. However, the GAL is realized when third-party libraries are called. NumPy backend, BLAS, LPAC, and CUDA generally make use of thread. NumPy calculations are therefore multi-thread by default. With Numba, it's also possible to release the GAL with passing the no-GAL equal true option. So, in fact, NumPy should be considered in two parts: front-end with the Python API, and backend. The most used is BLAS LPAC in C Fortran. Multi-threading relies only on the backend. Since there are several backend solutions, MKL, OpenBLAS, Netlib, and several versions, multi-threading functions are not listed in the NumPy documentation. Thread control by default, all cores are used. The value can be set with the environment variable associated with the installed multi-core library, such 1MP numthread or MKL numthread. We will compare two backends, MKL and OpenBLAS, with two versions of NumPy release, 2.2 and 1.26. On the slide, we have the installation command with CUDA. And we will compare also with 1 and 3 threads. The result is expressed as a speed gain compared to the reference version, NumPy 2.2 with OpenBLAS. Result 1 means the same time of processing as reference. I use i7 Intel processor with 4 cores designed in 2021. There are 6 tests: fast Fourier transform, scalar product, linear combination, log function, cumulative sum, and the search of the max. As we can see, only MKL backend take advantage of multiprocessing. It's also faster. It's also faster for A50. On the other hand, the search of the max with this backend is 2 times slower. Else, with one third, results are close. Now we will test the performance of the Intel library, which fully re-implement NumPy API. It's a DPNP Intel library for data parallel extension for NumPy. Can be run on the Intel CPU and GPU. This is the real advantage of our NumPy can be used GPU. Not yet in release major one, here version 0.17. Backend is 1 MKL Sycl BLAS, 1 MKL Sycl LAPAC, and the coverage of the function it's good. So the result, we have the best result for the sum of the vector, right? Else, bad performance for the selection of processing, to be confirmed with a newer Intel processor. The presentation of the key point of NumPy is finished. Now Alice will tell you about the Numba library.
Thank you, Jean-Marc. So now that Jean-Marc has presented the NumPy in detail, we're going to see how we can further optimize our code when we have written it with Python and NumPy. So Numba is a good tool to optimize parts of your code. It's a just-in-time compiler that translates Python and NumPy functions into optimized machine code. And for this, it uses LLVM. With Numba, you can optimize for different architectures. So you can optimize for sequential, multi-threaded, CPUs, GPUs. And so when you compile with Numba, you can approach the performance of C and Fortran code. However, Numba works best for code that uses arrays and NumPy functions, as well as loops, and the rest is not supported. So you cannot use it with any code, with every code. So how does it work? This JIT compilation in Numba. So for a function that you want to compile, you just have to put the @JIT on top of it. It's a decorator. And then Numba will read the Python bytecode for this decorated function, and it will combine it with the information about the types of the function's input arguments. And it will analyze and optimize the code. And finally, it uses the LLVM compiler library to generate a machine code version of this function that is adapted to the capabilities of the CPU and to the type of the arguments. And so this compiled version is going to be cached and then used each time the function is called. When you compile a function with Numba, at the first use, it will be very slow because you have to have the time of compilation and putting into cache. But then when you use it afterwards, the subsequent uses will be much faster because they will use the machine code that is cached. To JIT compile, you just have to add decorators to the functions or the loops that you want to optimize. And there are some useful options that we put here. So for example, the NoPython option is commonly used, and we'll see afterwards what it means. And you can also use the parallel equal true or the fast math equal true options to further speed up your code. What is this NoPython mode? Well, in Numba, there are 2 different modes when you use the JIT decorator. And the NoPython mode is the mode that we recommend for performance, because when you use this mode, you compile the decorated function so that it will run entirely without the involvement of the Python interpreter. So this leads to the best performance. But it can crash because if Numba cannot compile your function, it will crash and tell you need to change this function. So for example, if you call a function from another library than Numba can crash and tell you, I cannot compile this function. So it requires a bit of code refactoring so that everything in your code is either Python or NumPy. Before, in the previous years, the NoPython mode was not the default. It was the object mode. So at this time, if your compilation in NoPython mode failed, Numba would still compile using object mode. Now it only does it if you set no Python equals false. And so in this object mode, the only thing that will be compiled is the loops, and the rest of the code will be run in the interpreter. So then you still have a code that works, but it's going to be very slow, and you won't know really why, because it won't tell you which function you didn't manage to compile. So it was a previous default when you use JIT. So if you see codes from the previous years, you can see a lot of @njit, which is a shortcut for @JIT no Python equals true. But now it's not needed anymore because it's not the default. Another thing that you can use in Numba is the multi-threading, and it relies on the automatic parallelization. To use it, you just have to specify parallel equals true in your decorator. And to, for example, parallelize a for loop, you use p-range instead of range in these for loops to indicate that they can be parallelized. So it's very easy to use, and it's worth the test to see if it will speed up your code or not. So what can we expect in terms of performances from Numba? First of all, as I said, you should only use it when you have code that is made up of numpy arrays, numerical algorithms, for loops, and numpy code. It's very good for scientific calculation if you don't want to do other fancy things. You can also use it to create missing numpy functions. So, for example, to compile a part of the code that you want to, when you want to have a vectorized version of it, and numpy doesn't provide it. But yeah, the main limitation is that it can only be used on Python or numpy code. So if you want to use another library like matplotlib or I don't know, anything else, SciPy also, it's not going to be supported. So it can ask for a lot of refactoring of your code if you use other libraries, and you have to do without them. So since the first execution of the function in Numba is very slow because there is the time for compiling and caching the function, it's best to use the timeit module when we want to measure the performance of the functions we optimize with Numba. Because the timeit module will measure several iterations of the execution, and so it will smooth out the time spent compiling during the first iteration. And what's said when using Numba is that you can have compared to a NumPy code, you can expect like a 1.5 or 2 performance gain. And compared with just Python without NumPy, you can expect like 200 performance gain of 200 because, well, Python only is very slow. Okay, so let's see an example that I pulled from the Numba doc. So it's just a function that is going to compute the trace of a matrix. So we use the module timeit, as you can see with the % timeit. It's in a Jupyter notebook. And so we time the function without Numba. So it's 21 microseconds. You can see that timeit automatically chooses the number of iterations that it needs to do. So here it did 7 runs. And then if we did compile this function, so here with the njit decorator, but you can put jit, nowadays it's equivalent. So if we compile with Numba this function, then the result is squared in red. It's 3 microseconds. So it's 7 times faster. And it's just a for loop that we managed to optimize. And also in this timeit output that you can see, it's indicated that the slowest run took 7 times longer than the fastest. So this is the indication that Numba cached a result, and its normal is what we expect. So it compiled in the first iteration, cached the machine code, and then on the other iterations, on the 6 other iterations, it used the cached code. So it was much faster. Okay, so that was it for this Numba introduction. So as a conclusion of our webinar, we can say that Python was developed and popularized for its flexibility and ease of learning, but not for its performance because it wasn't created for it. However, it's still possible to do scientific computing in Python thanks to its vast ecosystem of optimized libraries. The basis of scientific computing in Python is to use NumPy always. This is the basis of vectorization in Python. So on the next slide, you can see that, as Jean-Marc explained, you have various backends on NumPy, which can, when you choose these backends, you can enable further optimization. And when the code lends itself to it, Numba can achieve performance close to that of machine language. So all this relies on NumPy, and the NumPy API has been cloned for a number of libraries, like SciPy, for example. And notably for GPUs also, it has been cloned. And for example, in JAX, in compare numerics. And this we will cover it in the webinar in 3 weeks on the 5th of June, when we will talk about Python for GPUs. So I hope you enjoyed this webinar. Please ask your questions in the Q&A channel. And well, we have some time to answer your questions, so go ahead. Thank you.
Thank you, Alice and Jean-Marc. So I will see if there is... Okay, there is one question for now about the uncertainties, because they are really, really high on the timing. But maybe you can precise the size of the arrays that you use for this example. Maybe it will clarify it.
I don't remember. I have a notebook. I can share this notebook, and I think I use a very large array.
Strange to have these uncertainties on a huge array. I was betting for the opposite, but it's normal to be high, because even once you access NumPy vector element by element, it's even slower than a list, because it's not designed for that. So it's normal. But it should be slow, but not with this uncertainty, in fact. Or maybe there is, you have...
I can share my notebook if you want.
Maybe instead of having just an uncertainty like this, maybe you can, maybe later, because now it will be a bit tough to do that right now, but I think it's better to see the distribution of the time that you have on your once you time your function. So you have the distribution of all the time, and you have a distribution, and I think we will see multimodal distribution, and in fact this I think this could explain the high uncertainties. Because as Adrien said before, and I will remember everyone at the beginning of the school, once you want to time a program, it's quite difficult to express an uncertainty, because you have generally multimodal execution. And so you have many peaks, and if you want to have an average, and you have to have a standard deviation, it does not mean much, as we are already familiar with Gaussian distribution or stuff like that. So maybe with a distribution, it will be as an extension of this presentation to feel what's going on. Do we have performance use case for comparison between broadcasting and Numba? That's a good question. Yeah.
So maybe I can answer. So I don't have a performance benchmark on my side. But usually Numba comparing to NumPy vectorization, you can have either the same performance, or maybe sometimes it can be slightly better. I don't know, Jean-Marc, if you have some things to add, but I would say, between 1 and 2 performance gain. Usually, is what they say for NumPy vectorization versus Numba.
Okay. One remark also for Michel. So I suspect that microsecond were in fact nanosecond for the uncertainties. I don't know, because I'm not sure that TimeIt is capable to go on nanosecond precision, but maybe they upgraded. I don't know. But for sure, nanosecond for TimeIt, maybe it's a bit too small. Okay, as we were talking about Numba, maybe I can bother with you, Alice, with a question. So you mentioned at the end of the presentation that NumPy has a lot of backend and a lot of library as using the same API also. Do you know which backend is used for the Numba parallel mode? Or can you change the backend, for example?
The Numba parallel mode, I'm not sure actually. I can check, but I don't think I ever changed the backend in Numba parallel mode actually.
Okay. Because I think for the vectorization, it's TBB.
Okay.
But for the parization, it's not really clear. So I assume it's maybe the same, but maybe we can change it. Maybe not. I don't know. Question from MG. Are there some good debugging and profiler tools for Numba?
Debugging and profiler tools. Okay, so I had to do a lot of debugging in Numba because when my code wouldn't compile, I had to do some change of the code. But usually the exceptions that they throw you are quite easy to understand, I would say. But I don't think I tried some specific tools for Numba. No, sorry.
Or maybe a classic GDB could work. Depends if you have a bug in the binary that you generate, or if you have a bug above. Maybe above with PDB it's okay, but inside the binary maybe you should use GDB or something like that. It's a guess. I don't know. I really don't know. But
in my use cases, I just with Python, I would say you mostly use the errors that they throw you, and then you fix your code. Because with Numba, actually, the errors are quite indicative.
Yeah, normally it's enough.
Yeah,
you should be okay. Okay.
Profiler tools, I would say PySpy should work actually because.
Yeah, normally yes.
It's a sampling profiler. I would say it should work. Yeah.
Oh yeah, we are still on Numba, so why not? Yeah, you show some performances with really small matrices, so you can show that Numba caches the compile library and everything is fast, and the compiling is done once. Did you try with larger matrices to evaluate the speed compared to classic C++ Rust Fortran implementation?
Yeah, sure, but I don't have the slides here. But for the Python,
For the school, maybe?
for the school, yes,
Yeah.
we have to use much bigger matrices.
Yeah, it's a teaser.
I would say, I think in our case, it's much faster than the numpy version. Well, much faster, yeah, maybe 1.5 or 2. Yeah, I think I didn't have any problem with large matrices with Numba.
Okay. Another question from MG. Is NumPy or Numba supports atomic addition like OpenCL? So maybe you want to...
Atomic addition?
Yeah, what do you mean by atomic addition? You want to sum only one element, or you want to sum a part? Ah, yeah, it's why. And so yeah, so you want to sum only with a condition. I never use that, so I don't know.
Yeah, me neither.
Yeah, generally, yeah, NumPy and Numba, they are designed to be used with global operation. So you want to use the same stuff around all the elements of your array, or maybe a part, but a big part, a full row or something like that, not one element. Maybe you can do it, but maybe it's not as fast as it could go, but you are not supposed to use it like that. So not just a question from MG. Numba will support this for GPU, but for CPU?
So I guess it was the same question as before. So
yeah, I guess also.
Yeah. These atomic additions work for GPU apparently, but yeah, for CPU, I don't know. I have to say I've never used it. Usually, yeah, I use the same operation on all the elements of the arrays.
Or maybe you should work on CPU, but
yeah.
Okay. So if there is no more question, I will try to find mine. Okay. For Jean-Marc, yeah, once you present transpose, swap axis, reshape, stuff like that, in fact, there is no real transposition made under the hood. So
yeah.
How can you make sure if, for example, you have transpose matrices, you want to transpose it, and you know for sure that it has to stay transposed for the rest of your computation because the computing will be faster in that case? How can you force the transposition to be realized? With,
you with a copy. You can do a copy with the transposition.
The copy will call the as contiguous array function? I didn't know that. Okay.
If you want to change the order, you can anymore use a view. So you must use a copy.
Ah, so the copy will realize the view. Okay, I didn't know that. Good to know. Because me, I use as contiguous array to be sure, but okay, it's good to know. Oh yeah, also for you, Jean-Marc, for the slide 20, when you have different method for the broadcasting,
Yes.
you have different costs in the computing. Do you know why? Under the hood, why sometimes it's faster? Because here it was quite the same value. Of course, the naive version is slower, but
which number slide? Slide number?
I think it was 20.
20.
But for the transpose or for the broadcast, it's also valid for cushion. But if you don't remember the size of the arrays, it will be difficult to answer. But
yes. In fact, the solution with reshape the big array or add a new dimension are very close for this example.
Yeah, but I don't understand why.
Yes. Sometimes it's very surprised.
So maybe it's about the size. I don't know. Maybe your matrices are fit in the L1 cache. So
yes,
could be a reason.
Rearrange the memory very fast.
Yeah, the same question also for the broadcast. Yeah, this one, because yes. once you transpose, so here you have a view for the transpose of your matrix for yes. the broadcast simple AV with a transpose plus V.
Yes.
So you don't realize the transpose, and I think I don't know what's going on under the hood in NumPy, but I think normally should be better because you want to sum a full row with one element. It will be faster than to transpose and then sum the rows with the full vector and then reiterate the full vector and again and again and again. So we'll have less read without the realizing the transposition. But it's still slower than the other method. It's quite close, in fact, but it's not really in the uncertainties. But again, maybe with the detail of the distribution, it will be easier to understand. But
yes, effectively, sometimes the result of timing is hard to understand.
I don't know if you can, with timeit, extract the detail of all the measures that he did. But at some point, it will be interesting to plot the histogram of all the little times that it has to perform this computation.
Yes.
Because normally timeit is supposed to remove the very bad times. So once you initialize or something like that, if it's once over everyone. But yeah, maybe you have some. It could be interesting maybe to have a plot with you change the size of the matrices and you get the time of the computing to see how it evolves.
Yes.
So to understand, because maybe once I think maybe, or I can guess, if your matrix is smaller than the L1 cache, if you do not transpose, maybe it's not that problematic because you still you still pay the L1 cache access, but for a bigger matrix, you will pay the price if you kill one cache with one line. And if you transpose, you realize the transposition, you will do an out of core with the big matrix, but not with the small one. Without the transposition, you will do an out of core with both. That could be better for the prefetch and to not spoil your caches. So yeah, maybe it could be interesting to have a bit more. In fact, you will have much more time in the digital school, so it's normal. But yeah, to have this kind of nice distribution to understand what's going on. So there is no question from David, even if it's not written in the chat. What is the level you expect from your attendees on your school in terms of
yes.
Python? Do they know well Python or not well? Do they know well another language if they want to dive into Python? Or
So there are two classes, one on CPU and one on GPU for Python. With the one on CPU, you are going to write the Grace code and also do some tricks to make it faster. I would say it's more intermediate level. If you're really discovering Python, you might not finish the exercise, but it's okay because we give the solution also. If you're very, very efficient in Python, maybe but the exercise won't be as interesting to you, but we also will make some exercises for people that are more fluent in Python, I would say. And on the GPU class, then we will reuse the CPU code we made and we'll try to tweak it to use it on GPUs. So depending on the tools that we will use, it will be more or less easy. So I would say if you're really a full beginner in Python, maybe you will be able to follow a little bit, but you won't be able to write a lot. If you're intermediate, I think it's the right level to have. If you're an expert, maybe you will be more interested with the GPU course or the exercises that we are going to give on the CPU course, but it's going to be less central to the course.
Okay, thank you. Okay, we start to have the thanks in the chat, so it's time to finish. So of course we will have much more materials in the lecture, so with hopefully some distribution for the results. So it will be nice to interpret the results. So thank you for attending this webinar. So normally we will have the replay tomorrow afternoon, something like that, ready. So next week we will do some sorcery with Rust on GPU. So don't miss the lecture also. We'll see Vulkan, all the weird details of GPU programming. So have a good day and see you next week. Bye.
Thank you very much.